In a totally inelastic collision, the two objects that collide wind up sticking together. Based on the conservation momentum, what should the final velocity of the two objects be as a function of m1, m2, v1 naught, and v2 naught? So let's imagine that we have object m1 here, and maybe here is its target, object m2, and they're going to collide together and stick. Maybe to keep everything in a positive direction in like a standard xy coordinate system, or just standard maybe x axis number line type of thing. I'm going to give this one a rightward velocity of v1 naught, and then I'll give this one a smaller rightward velocity of v2 naught. But everything I'm going to do in terms of the analysis of this, my intention is going to be that it's going to carry over to even situations where maybe the one or more of the velocities is pointing to the left, which would in one dimension be characterized as like a negative x component, or if you're not worried about y components, you can just say, hey, it's a negative velocity, right? That's perfectly fine, turns out. But even if you were looking at a two-dimensional situation, it turns out this is going to carry over as well, but I'd like to simplify things by looking at this simple one-dimensional type of scenario. And the analysis I'd like to apply to this very kind of abstract imagined system of two particles having a totally inelastic collision is conservation of momentum. My argument is that there are no other forces applied to these two objects simply because I haven't put any of them in there. I haven't really said what any of these things are, right? So I'm just saying there are no other forces other than the fact they're going to crash into each other and stick together. There would be forces between the two objects involved with that, but I'm not even getting into any details on like what the nature, like is there Velcro? Is it something else that makes them stick together? I don't care. I just know that they stick together. But what I know is that if I look at the combined system of M1 and M2, if there are no external forces, and even not knowing the details of the forces of interaction between these two particles, those are internal forces, so the net force is going to be zero on the system, which means that momentum is definitely conserved. And based on the idea that after they've collided with each other, they're going to wind up sticking together. So if I kind of like draw like maybe one point and here's another point, right? This is like M1 plus M2 stuck together now, and now they're moving together at some different final velocity, and maybe I could label that as just V. I could label it as V1 or V2, but since they're stuck together, it's the same, so I feel like I don't even need a subscript there. But that's going to help me to figure out how to put in some of the details on P final and P initial, because P final, I think, since they're stuck together, I can just look at that as like one object with a total mass of M1 plus M2 and a velocity V. And since I wrote this as a vector and I said I'm going to try to do this without any like loss of generality, I'm just going to write a vector symbol here. But even if you didn't include that and just said, okay, whatever, this is the picture I'm doing, it would have made sense, right? But it turns out with that arrow there, you could apply it to any even more complicated situation, and that'll be fine. But let's look at the initial momentum. For that one, we have two objects, each with their own momentum. So for the object M1, its momentum would be characterized by M1 V1 naught. And if we were working with explicit signs, the fact that both of these point to the right, and in particular this one points to the right, it would be okay to make this positive. But I'm going to go kind of implicit and just put a vector symbol up here. So that means any direction is implicitly attached to that quantity. And then I'm going to add M2 V2 naught. I think what I'm trying to say with all that is, like, if you just removed all these arrows and said, would it still work? The answer is yes. If any of these objects, though, were moving to the left, what would you have to do? Well, you'd have to put an appropriate minus sign in order for things to work, but I'm just covering that direction with these arrow labels. That's maybe a simple way of saying what do they mean to me or to anybody else. And in more advanced math classes, you can get into more details of how you could do that with advanced notation, but we're not doing that. Anyways, my goal, though, simply, it says, what should the final velocity of the two objects be? So I'm just going to solve for this. I think the reason why I'm talking about, like, don't worry too much about these vector symbols is we've rarely in this class done actual manipulations of vector equation. We've usually just said, here's a vector equation, now use it as a guide and do stuff with components. But we've not really done any algebra with vector equations, and so that's maybe a little bit jumping past like the level of math we're supposed to do. But in this case, all I'm going to do is divide both sides by the total mass. And so if you just imagine that the vector symbols weren't even there, we're just going to do it as if, as if it were like that, right? In other words, dividing two sides of an equation by the same thing is something we all know how to do, right? And in this case, if I'm dividing by m1 plus m2, on the left side, that naturally canceled the m1 plus m2 that was there. So now I have this v isolated, and this v, again, represents the final velocity v. I could say this is the solution for v1, or it's the solution for v2, but since they're stuck together, again, it's the same. So this formula suffices then for an answer. And the thing to notice, this kind of the connection to the key concepts page, is this is the center of mass formula. For whatever reason on the key concepts page, I'd subscripted things a little bit different. Like I didn't have v1 naught, I just had v1. And I think the reason why is because really for an inelastic collision, even if you remove these knots, it would still make sense, because you've basically got v1, v2, the individual velocities of the two objects before they collide, and then you've got one velocity describing them after they collide, which I think in the key concepts page I just still labeled that as VCM, because this is VCM for this system. And so there it is, and that's, if you look at this answer, I've subscripted it here like V final equals VCM. Another way of looking at this is to say, since this is a system where momentum is conserved, the velocity of the center of mass really is a constant thing for this process, because since momentum is conserved, the net force is equal to 0, which means the acceleration of the center of mass must be equal to 0, because we said before the net force for a combined system really just relates to the acceleration of the center of mass if you have more than one object in the system that are moving differently.